Welcome to videos on linear integrated circuits. So in this video, we shall see an important topic, phase lock loop. So let us first have the introduction of phase lock loop. The motivation for PLL, why we are studying this phase lock loop. So we know that it is easy to detect the variation in the amplitude of a signal, meaning if there is a changes in the amplitude of the signal, we can have a peak detector or we can have an envelope detector. We can easily find out the variation in the amplitude. So a peak detector is one where you have a diode and a capacitor, and in an envelope detector we have a diode, a resistor, capacitor, where you can easily trace the variation of the amplitude of a signal. As it is mentioned here, envelope detector will easily detect the variations in the amplitude of a amplitude modulated signal, which is an AM signal. Think of detecting the variations in the frequency of a signal, that is a frequency modulated signal. So you have a signal where the frequency is varying. So if you are asked to find out the variation of frequency, it is not so easy as in case of amplitude variation. Now it is a difficult task to find out the variation in the frequency of the signal. Now to detect the frequency variations in a FM signal, it is necessary to compare and trace the phase of the input signal with a reference signal. So now if you want to actually verify the variation in the frequency of an FM signal, which is a frequency modulated signal, it is necessary to compare and trace the phase of the incoming FM signal with a reference signal. Now we need to have a reference signal so that you can compare its phase with the incoming signal having some frequency variation. When you compare, then only you can able to trace the variations in the frequency. If it is possible to extract the phase difference of the two signals, it is possible to detect the frequency variations. Now we know that if we can able to extract the phase difference between this reference and the incoming signal, so then you can somehow trace the variation in the frequency. So that's why if it is possible to extract the frequency difference of the two signals, which is the reference signal and the incoming signal, then it is possible to detect the frequency variations of the input signal, because you will be having a control over the reference signal. If you can able to find the difference between the reference signal and the incoming signal, then it is possible to detect the variations in the frequency. Now let us see how does a PLL looks like. Now PLL, which is known as the phase lock loop, is a circuit used to trace the variations in the phase and the frequency of an incoming signal. So using PLL, you can actually trace the variations in the phase or the frequency of the input signal. In order to do so, a reference signal is generated within the PLL. So PLL is an circuit where you'll be generating a reference signal within the PLL circuit. Now there is a mechanism within PLL to vary the reference signal frequency if the input signal frequency and the phase deviates from the reference signal. Assume that you already have a reference signal. So there is a mechanism available within the PLL to vary this reference signal frequency if the input signal frequency changes its phase and the frequency deviates from this reference. So reference signal is having some frequency. Assume that if your incoming frequency changes, so there is a mechanism available in PLL to change the frequency of this reference also as your input signal changes. As the input signal's frequency or the phase changes, the mechanism will vary the reference signal's frequency and phase such that their difference is zero. So what is the motto behind this is, as the input signal frequency or the phase changes, there is a mechanism existing in PLL to vary the reference signal's frequency and the phase so that there is no difference between the incoming frequency and the reference signal. So this mechanism is very important. So the mechanism available will actually make the difference between the incoming frequency and the reference frequency zero. Meaning there is a mechanism in PLL to trace the variations in the input signal frequency and phase by locking it with the reference signal's frequency and the phase. Now, how you are actually tracing it is, so there is a mechanism available in PLL to trace the variations in the input signal frequency and phase by locking the incoming frequency with the reference signal frequency and the phase. So this is very important. So there is a mechanism available within PLL to actually trace the variations of the input signal with respect to the reference signal. Now this is the block diagram of a PLL. So you can see this Vi having a angular frequency omega I and a phase of theta I. It's given to a phase detector. So the other input for the phase detector is coming from this voltage controlled oscillator. So this is a circuit which is going to give the reference signal. So having an amplitude V0, having an angular frequency omega naught and theta naught is the phase of this reference signal. You can see this phase detector is the one which actually detects the difference between the phase of the incoming signal and the reference signal. So there is a VD which is coming, which is actually the indicating the difference between these two input and the reference phases. And this VD, whatever the difference that is obtained, will be passed through a loop filter, which is usually a low pass filter. This low pass filter will give a output voltage VE, which is known as the error voltage. Now this error voltage is applied to this voltage controlled oscillator. We know that voltage controlled oscillator is one whose frequency can be changed by an external voltage. Now this error voltage is going to actually change the frequency of this so that this VD becomes 0. So it was said in the previous slide that there is a mechanism available in PLL to make sure that this incoming frequency and this reference frequency are actually tracing each other. I can see whenever there is a change in the input frequency or the phase, so it will generate a difference of this with respect to in comparison with the reference signal. If there is a positive variation, now there is a error voltage generated so as to make this omega naught close to omega I, so that this becomes 0. So this will be keep on there in the loop. So this mechanism is the one which is very important. So this signal which is applied to VCO, that is voltage control oscillator, will actually change the reference voltage frequency to match it with the incoming frequency. So let us see how does each block is going to work out here. What is the function of each block? So this is the phase detector, a loop filter, and a voltage controlled oscillator. Now VCO, this is the voltage control oscillator, is nothing but a freewheeling frequency generator having a frequency omega naught, and this depends on the voltage VE. So assume that V is equal to 0. So this will be running at a freewheeling frequency of omega naught. If this V changes, if the V is positive, the frequency increases. If this V is negative, the frequency reduces around omega naught. Now let us see what is the phase detector function. This phase detector block, the output voltage is VD. This is proportional to the phase difference of the input signal Vi and the VCO signal V0. So this VD is proportional to the difference in phase of theta I and theta naught. And this loop filter is a low pass filter to remove the noise that is there in this VD, so which is proportional to the phase difference of the input and the reference signal. Let us see how does a PLL works. Assume that VCO, that is V0, is oscillating with a freewheeling frequency of omega naught and a phase theta naught. And assume that input signal Vi has a frequency omega I and phase theta I, which is same as the frequency and phase of the VCO waveform. That is, assume input signal is exactly same as the reference signal in terms of both frequency and the phase. As there is no difference in the phase, Vi and V0 are same, the phase detector output is 0 volt. So there is no detection happening because there is no difference. The output voltage is 0. Now this VD is filtered using a loop filter, which is a low pass filter, and there is an output voltage V called the error voltage is applied to VCO. Now in this particular case, since the error voltage is 0 here, the VCO will be getting no correction, so it operates with the earlier frequency of omega naught, so it will be keep tracking the input signal. Now let us assume that this error voltage VE of 0 represents no difference in the phase of VI and V naught, because this is 0 means, so this VE of 0 is coming from the VD passing through a low pass filter. Since VD is 0, VE is also 0, this indicates there is no difference. When V is equal to 0, VCO output is frequency frequency will not be modified. So as I said earlier, since this V is equal to 0, this omega naught of t, so this t is nothing but this is with respect to time, so it is already oscillating with the frequency of omega naught. So this omega naught will be changed depending on the value of error voltage. Since the error voltage is 0, so this remains in the previous frequency of omega naught, where this k naught is given by the sensitivity of VCO, which is given in terms of radians per volt, sorry, radians per second per volt. Now suppose if there is any variation in the input signal frequency in the phase with respect to the reference signal phase. Now you can see, let us assume that this VI deviates from the reference signal. Then phase detector detects the changes in the phase and it generates output voltage proportional to this phase difference. Now you can see this VD of S is nothing but KD, which is a constant, multiplied by the difference in the phase of the input and the reference voltage. So this output of the detector is proportional to the difference in the phases. Now this phase detector output is filtered in a low pass filter, and its output voltage which is VE, that is error voltage, will be used to vary the free running frequency of the VCO such that the error voltage is reduced to 0 volts. Meaning whenever there is a variation in your input signal happens, so your phase detector actually detects that variation, and that output is applied to the loop filter. Loop filter will actually give an error voltage of VE. Now this error voltage VE is proportional to the variation or the deviation in the phases of the input and the reference. Now this generated error voltage will be applied to VCO to change its frequency so that the error voltage becomes 0. So the VCO frequency will be changed in accordance with the error voltage so as to make the reference signal frequency same as that of the input signal frequency. Now this error voltage produced is a measure of deviation in the phase of the input with respect to the reference signal. So if the error voltage is more, then the deviation is more. If the error voltage is 0, meaning that there is no difference between the input and the reference signal phase as well as the frequency. Suppose if there is any variation, so it can be either plus or minus in the frequency or the phase of the input signal with respect to the VCO signal, then VD will not be 0. Hence the error signal VE will be used to adjust omega naught till V naught synchronizes with VI. That is, until for every one input cycle, so there should be one and only one VCO cycle. So this condition is called PLL is locked, that is V naught is equal to VI. So carefully observe this. So whenever the input voltage makes a deviation with a positive sign or negative sign, then the VCO, the phase detector will generate a signal VD which is not 0. Hence this error signal, which will generate an error signal, this error signal is applied to VCO to adjust the frequency of the VCO such that this exactly coincides with the input voltage. So then we say PLL is locked. So this is a very important concept. PLL should be locked to trace the variations.